All right, so let's do this. We're going to start in on our new chapter. This is going to be chapter 16. Okay, and we're going to talk about reactions of benzene and benzene derivatives, a class of reactions called electrophilic, aromatic, substitution, or EAS for short. All right, and our key word here is this substitution. All right, unlike alkenes that undergo addition reactions, aromatic compounds do not undergo addition reactions, right? So for example, we took cyclohexene, we would react that with, for example, HBr, and we would get the addition product, where the hydrogen gets added to one side of that double bond, the bromine gets added to the other side. Again, this is what we would call an addition reaction. So this is our addition product. All right, but if instead of starting with cyclohexene, we started with a fully conjugated ring, our benzene, okay, since benzene is just a bunch of double bonds, we might expect to get this addition product here, but this does not occur. This reaction does not occur. Why would that be? If we look at our product here, what is so unfavorable about our product compared to our reactant? Remember that magical classification that we did last week of aromatic, non-aromatic, and anti-aromatic. My product, or rather my reactant, is an aromatic molecule, benzene. But if I look at my product, what would we classify that as? This product that doesn't occur. Is that aromatic? No, we don't have a fully conjugated ring, so that would be non-aromatic. So if benzene were to undergo an addition reaction, it would have to break its aromaticity. It doesn't want to do that. It wants to stay nice, super stable aromatic compound. So instead, these addition reactions don't occur. Instead, what we're going to see are substitution reactions, where the hydrogen on our benzene ring is going to be replaced with some electrophile. All right, so an electrophilic aromatic substitution reaction. So we don't see any addition product. Instead, we're going to see our substitution products. All right, we're going to look at sort of a generic reaction mechanism here for these, and then we'll look at specific electrophilic aromatic substitution reactions. Okay, so again, unlike alkenes, we don't have any addition product. Instead, we're going to see these substitution reactions. All right, so our EAS mechanism. Okay. Again, here's where we're going, our substitution product. Okay, the first step in the mechanism is indeed what you would expect based on what we learned about alkenes. Our nucleophile in this reaction is going to be that pi bond in benzene. That's going to reach out and attack that electrophile. All right, my base of my arrow is starting at a pair of electrons. It's ending at this atom. Again, we'll see what our specific electrophile is here. But everybody take a second and draw me my intermediate in this reaction. So now I have a new carbon bond to my electrophile. Importantly, that carbon still has that original hydrogen bound. All right, and then what am I going to need to include on my intermediate here? Something's missing. Charge, all right? And so importantly, whatever carbon you're going to put that electrophile on, its neighbor is the one that got its octet broken, right? There's my positive charge on the neighboring carbon. Okay? So in the last step here, we need to reform our aromatic compound here. We need to reform our pi bond. So importantly, where does that pair of electrons come from? It was what was keeping that hydrogen attached. All right. In general, we don't like hydrogens to just go flying off into space. We're always going to have some base, and I'm just going to use generic B here for my base to be my proton acceptor. All right, the identity of the base will depend on your reaction conditions, but again, we don't just have hydrogens flying off. They're always accepted by something, what we call a base, right? That's a hydrogen acceptor as a base. All right, and then we've reformed our nice aromatic compound here. All right, and so we can see we've replaced the hydrogen that used to be on that carbon with some electrophile here. All right, so all these reactions are going to have this same basic mechanism. Now let's take a look at a few specific electrophilic aromatic substitution reactions. All right, so we're going to make a list of our electrophilic aromatic substitution. Okay, and the first one is going to be a halogenation reaction. Okay, starting out, let me copy a benzene ring here. Okay, so you can use either chlorine or bromine, either one would work. Let me put this up here. We're going to use bromine as our example, but I'll say it at the top. Cl2 or Br2. Okay, everybody take a second. What would my product be here? What do we assume is going to be our product? Again, we got to have our benzene ring. We're not going to ruin our benzene ring in the process. All we're going to do is replace that hydrogen with that halogen. So in this case, my bromine. Okay. Now, importantly, all of these reactions we're going to see are going to require some sort of a catalyst. Benzene is going to play the role of our nucleophile, but all things considered, it's a pretty crap nucleophile. right? Those pi electrons are very happy bouncing around that ring as an aromatic compound. They're not all that terribly nucleophilic, which means we need to have a catalyst in there that's going to make our electrophile into a really good electrophile, right? Again, benzene, kind of a crappy nucleophile. In order for this reaction to actually work, we need a really good electrophile in there, all right? So our catalyst is going to be aluminum bromide, or you would also maybe see iron 3 bromide. All right, but importantly, this is going to turn our electrophile, that bromine, into a much better electrophile than it is all by itself, what we would call the electrophilic species in this reaction. Okay, and what happens is that bromine ends up forming a complex with that metal compound that would look something like this. So here's my aluminum. It's already got 3 bromines on there. All right, but then what happens is it's going to now form a complex with our Br2. And this is now a much more electrophilic bromine here on the end. All right, I got to be good with my charges here. My halogen in the middle has 2 bonds and 2 lone pairs. So that's how you would draw bromine with a formal charge of +1. And that aluminum, having accepted that extra pair of electrons, has a formal charge of -1. Okay, so it turns out that bromine all by itself is not a good enough electrophile for this reaction to actually occur. If you just mix in bromine with benzene, nothing happens. But if you put in this catalyst, like our aluminum bromide, it will form a complex with that bromine molecule, making it that much more electrophilic. So this is actually what's participating in our reaction here, this electrophilic species. All right, cool. All right, so we can do our halogenation reaction. Our next one is what's called a nitration reaction. Okay, again, we're going to start out with our benzene ring. All right, so for a nitration reaction, use nitric acid. Okay, and this creates what's called nitrobenzene. Everybody take a second and see if you can't remember what that nitro group would be. So that's that NO2 group. I'm going to draw out the Lewis structure here, just to be clear. My nitrogen would have a formal charge of +1, and my oxygen, my single bonded oxygen, a formal charge of -1. Okay, but likewise, these reactions always have some sort of a catalyst in there. For your nitration reaction, you add nitric acid in the presence of a strong acid like sulfuric acid catalyst. Okay, This creates the following electrophilic species. All right, that strong acid will dehydrate that nitric acid. Creating this electrophile here, this nitrogen dioxide, where that central nitrogen has a positive charge. So again, very electrophilic species, right? Very electron poor species. This thing is what will actually react with our benzene ring. All right. Our next one is what's called a sulfonation reaction. Okay, so here we have our benzene ring. It's going to react with H2SO4, all right? But importantly, you have to boil that H2SO4, what we would call fuming H2SO4. And importantly, it's the fumes that will react with that benzene molecule. All right, this will create what's called a sulfonic acid. Put an SO3H group on there. All right, importantly, just to kind of have this all drawn out with our Lewis structure, you have your sulfur in the middle. It's got two oxygens double bonded, and then an OH group, and then a hydroxyl group. Okay, this is what's called a sulfonic acid, or sulfonyl group. All right, and our electrophilic species, similar to what happens with our nitric acid, we have a dehydration. That leaves our sulfur relatively electron deficient. All right. Cool. So the next two are named after the scientists who discovered them, what are called Friedel-Crafts reactions. All right, these are particularly sort of powerful in that they create new carbon-carbon bonds. Okay, so we're going to add some carbons to our benzene ring. All right, so the first would be a Friedel-Crafts alkylation reaction. So in an alkylation reaction, we're going to take an alkyl chloride. So we'll just use a simple one here. chloromethane. All right, and importantly, that sticks that methyl group on that benzene ring. All right, this will use that aluminum chloride catalyst. Okay, and what the aluminum chloride does effectively is to pull that chlorine off of that carbon, leaving you with a carbocation. A nice, great electrophile, right? Again, electrophile is electron deficient. You don't get much better of an electrophile than a carbocation. Okay, so our electrophilic species is that carbocation. All right, now we got to be careful here because our carbocation intermediate, whenever we have this carbocation intermediate, we got to watch out for what when we're doing our reactions? Methyl shifts or hydride shifts, right? And we're going to have the same thing here. Just like every other reaction with that carbocation intermediate, we're going to sort of make a note here. We need to watch out for the shifts, for the hydride and methyl shifts. All right, those do indeed occur with these Friedel-Crafts alkylation reactions. All right, and then our last one here is a Friedel-Crafts, what's called an acylation reaction. Okay, so an acylation reaction. Instead of using an alkyl halide, it's going to use what's called an acyl halide, which is when you have that halogen bound to a carbonyl carbon. All right, you again use that same aluminum chloride catalyst. All right, and this will again create a carbon-carbon bond, but specifically to that carbonyl carbon. So in this case, I got 3 carbons on the end here, but importantly, my new bond is between benzene and that carbonyl carbon. Right. In this case, what that aluminum chloride is doing is that thing that we saw in our previous reaction. It's going to remove that chlorine and leave you with a carbocation. But now our carbocation is specifically our carbonyl carbon. These things have a special name, and I'm blanking on it to be perfectly honest, all right? But nonetheless, what we can say is that unlike our regular carbocations, we do not have to worry about this thing rearranging itself. That positive charge will always stay on that carbonyl carbon. So we can just say we do not have any shifts that we got to watch out for. All right, so we got these 5 reactions that we've just discussed here. All right, and so first we're going to make a little summary wheel here, but I just want to kind of tell you the punchline. Each individual reaction we definitely have to know, right? We have to know what we would call the substrate reagent product combinations. If I give you this substrate and this reagent, you got to tell me what product it is. If I give you this substrate and this product, what reagent did you need to do it, right? So for these reactions, we need to know our substrate reagent product combinations, okay? But the name of the game here isn't just going to be each individual reaction by itself. What we're going to see is that if we do multiple reactions, we do pick two and we do them in a certain order, we're going to get a particular product than if we change that order, all right? So each individual reaction by itself, we got to know that. But then what we're going to do is we're going to start mixing and matching these reactions together, all right? So before we move on to complicating things, let's just go ahead and summarize everything that we just did. We're going to create this little wheel here. All right, and we'll put each of our 5 reactions on a little spoke of this wheel. So we have everything all summarized next to one another. All right, so we have our halogenation reaction. We did this with bromine before. Let's just do it with chlorine for the sake of practice. We can do either a iron or aluminum chloride catalyst. All right, we have our nitration, our sulfonation reaction. And then we have our 2 Friedel Crafts. Cool. All right, everybody take a second and fill this wheel out here. Just kind of summarizing everything, stacking all them next to each other so we can see all that we can do. All right, so there's 2 more reactions that we're going to learn, and these ones are sort of how to modify one of these existing groups here. All right, so the first one is going to start with nitrobenzene. Okay, and this is how we can reduction of nitrobenzene. Right, so our reagents that we need to do it is first you treat this with zinc in the presence of a strong acid like hydrochloric acid, and then strong base conditions. Okay, and this will have the effect of reducing that nitro group from being NO2 to just being NH2. Okay, and we got a special name for this thing here. That's one of our special benzene derivatives. So this would be taking nitrobenzene and turning it into aniline. All right, so let's just sort of add this to our wheel here. Now we know how to take that nitrobenzene that we just created and reduce it to aniline. Okay. All right, we're going to add one more here, but let's just take a look at why. All right, so let's say that we're going to start out with benzene. Okay. I want everybody to take a second and give me the product of treating benzene with 2-chloropropane. Okay, so that is going to put those 3 carbons on my benzene ring. All right, and importantly, it's that middle carbon that gets attached to my benzene ring. So why is that? Let's remember, let's draw our electrophilic species. All right, well, that aluminum chloride is going to remove that chlorine, leaving us with a carbocation. All right, cool. Then we're going to do the same thing, but now instead of 2-chloropropane, we're going to pick 1-chloropropane. All right, and I want everybody to take a second and give me my product of this reaction. right, so by analogy of what we did last time, you would say, okay, I'm going to attach my benzene ring here. Okay, it turns out though, this is the minor product in this reaction. What would the major product in this reaction be? Let's draw our electrophilic species again. Okay, I'm going to remove that chlorine and put that positive charge. But what's going to happen to our carbocation intermediate here? It's going to do one of those shifts, right? In this case, we're going to have a hydride shift. So one of these hydrogens from a neighboring carbon is going to jump ship to that positive charge. And what we're going to get formed is the more stable, more substituted carbocation intermediate. And this will lead us to our major product, which is the same as what we saw before. That branched alkyl group on there. All right, so our major product is that hydride shift product. So then this poses a problem here, all right? How do I attach a simple alkyl group at its primary carbon, right? What if I really wanted to make, for example, butylbenzene? I have my benzene ring, and I really want to create a benzene ring with a butyl group on it. How can we do it? All right, so what we're going to do is we're going to break this up into two steps. And first, we're going to create, we're going to do an acylation reaction. So not an alkylation reaction, but one of those acylation reactions. All right, we'll use an acyl chloride with the correct number of carbons. So if I'm trying to add a 4-carbon butyl group, I'm going to use a 4-carbon acyl chloride. Now I have my new carbon-carbon bond. I have my carbon attached where I want it. I just have that pesky carbonyl group there. All right, so our next reaction, oh whoops, and let me be good here. I also have my aluminum chloride catalyst still. All right, so the next reaction here, we're going to fully reduce that carbon, get rid of that carbonyl group altogether. We can do this using zinc, HCl, and heat. So if we really wanted to create an alkyl, put an alkyl group on our benzene ring, and we really want to attach it at that primary carbon, we're first going to do the alkylation reaction. And then we'll reduce that alkyl group. So we got our new reaction here using zinc, HCl, and heat. Okay, that effectively cleaves off that carbonyl oxygen altogether. All right, so again, let's just kind of summarize all of our reactions that we learned up on this wheel here. We got one more we're going to put on there, starting with that acylation product. Again, we got that same metal, zinc, HCl, but you just do it all in one step here. Zinc, HCl, and heat. Cool, so these are our reactions that we got to know here. We're going to start mixing them and matching them together next class, right? Turns out that the order in which you perform these reactions will impact what product you get, okay? For our remaining, I don't want to dive into that right now. We don't really have enough time to do it justice. What I do want to do is want to take a look at these different groups. It turns out that the reason why these different groups do different things is that some of these groups are adding electrons to the ring. They're making benzene an even better nucleophile. And others are doing the exact opposite. They're what are called electron withdrawing groups. All right, so let's just kind of illustrate this. Let's first look at an electron donating group. All right, and what we're going to see are that these are groups that add electron density to that benzene ring. So if you're adding electron density to benzene, are you making it a better nucleophile or a worse nucleophile? Are nucleophiles electron rich or electron poor? Nucleophiles have a lot of electrons. That's what they're doing, right? They are donating electrons in the grand scheme of your mechanism here. So if we're putting more electron density into this ring, is that a better nucleophile or a worse nucleophile? Better nucleophile. So these are going to be groups that if we have on our benzene ring, they're even better nucleophiles than just benzene all by itself. All right? So add electron density to the ring. These are creating better nucleophiles. All right, so let's take a look at one example. Okay, so we can spot our electron donating groups because they always have a lone pair directly next to the ring. All right, so this is how we're going to spy these electron donating groups. They have a lone pair that's next door to that ring. All right, and what's that lone pair going to do? Just like the name suggests, what we're going to do is we're going to draw some resonance structures that show that that lone pair is getting donated to the ring, right? So I'm going to put that electron density into that ring here. Okay, now, I have to be careful. I can't stop there. What's the problem with if I stopped there? Let's just real quick draw what our product would be if I stopped there. That lone pair comes down. What's wrong with this intermediate? Everybody's organic chemistry brains need to be exploding right now. What do we see that's wrong with that carbon? It's got too many bonds, 5 bonds, can't have it, right? Illegal, boom. So I can't stop there with just my one arrow. I gotta also break that pi bond there. I got to kick that pair of electrons onto that neighboring carbon. All right, so now I have this intermediate here. And what's missing? Charge, and specifically what charge do I need to include in here? Negative, right? Remember your charges are notoriously difficult to keep track of. Remember your conservation of charge rules. You're starting out with something neutral. I better have a net neutral molecule in the middle here as well. I didn't add any charge to it or take anything away. So I have to have a negative charge in there. Importantly, this carbon right here that accepted that pair of electrons is then going to have that lone pair. Right? So here's my lone pair with that negative charge. Okay? Now, importantly, this isn't the only resonance contributor I can draw. I can keep on going, keep on bouncing that charge around the ring. Okay, so again, now I can have my lone pair come down here. Again, I can't break that carbon's octet, so that pair of electrons has to be kicked up onto its neighbor. All right, and we can play this game one more time. All right, that pair of electrons can come down and again bounce that negative charge to that last position. I'm running out of room. Cool. All right, and we'll pick up on this next time, but again, this electron donating group, it donated this pair of electrons to this ring, right? Making that benzene a better nucleophile. But what I want to sort of point out here is it's not making that, it's not spreading that charge evenly around that ring. It's only hitting specific positions along that way, right? Every other carbon is what's got that negative charge associated with it. So what we're going to see is that this thing is a better nucleophile, but will direct incoming groups to specific carbons, because it's those carbons that are better nucleophiles. Cool. All right, we'll pick up with this next time.